Still Dr. Altieri here. We've moved on now to Module 2, which is focused on chemical oceanography. And you'll see there's quite a few connections between chemical oceanography and some of the principles lectures, or some of the lectures from the principles module. In particular, today we're going to talk about the unique properties of water, which of course in the principles module, when we were talking about temperature and things like that, we also talked a little bit about the unique properties of water. So let's go into it a little bit more deeply now, because we're getting into the chemical side of things more explicitly. So water is a really interesting molecule. It has a variety of unique thermal and dissolving properties. Thermal, of course, meaning as it relates to temperature and heat. The dissolving properties are important, particularly for seawater, which is chock full of stuff. So seawater is mostly water and mostly water molecules, but there's a lot of dissolved substances in seawater. And when it came to salinity, and we talked about the 6 major ions that make up the largest fraction of the dissolved substances in seawater. And so as a result of this salinity, or the stuff in seawater, and the unique thermal properties of water, these all give rise to the ocean having interesting temperature, salinity, and density profiles with depth. So when you look at the properties at the surface of a part of the ocean, they can be very different than the properties below the mixed layer and then on into the deep ocean. The presence of water on Earth is largely what makes life possible. Most organisms are mostly water, us included. And it's the chemical structure of water that gives it its unusual properties. So yes, we're talking about hydrogen bonds again. So a quick refresher, back a little bit into chemistry. So this is your basic model of the atom. Atoms are the building blocks of all matter, and we're not going to get into sort of nuclear physics here, but there are subatomic particles. Each atom is composed of protons, neutrons, and electrons. Here on this figure on the right, you can see the electrons, the little yellow spheres with the negative charge in their orbitals. And then in the nucleus, you have your protons and your neutrons. It's the number of protons that distinguishes chemical elements. And protons are positively charged, whereas neutrons are neutral. So neutron neutral, proton positive, and then that leaves the electrons as being the negative. So a molecule is then a collection of at least 2 atoms held together by shared electrons. So it's the electrons that are the part of the atom that when they get together, you end up with a molecule. And this is sort of, as the text defines, the smallest form of a substance. So water is a molecule, and it is composed of 2 hydrogen atoms and 1 oxygen atom. So here we go. So water, our special molecule that we're still stuck on, can be represented in a variety of ways. This is sort of the simplest, where you've got the O atom and the 2 H atoms. This already is showing the bench structure, so it's not linear. And the bench structure results in this slight negative charge by the oxygen and this slight positive charge hovering around where the hydrogens are. This image over here shows it a little bit slightly more realistically, because it includes the sort of cloud model of the atom. And you can see again the oxygen and the 2 hydrogens with their slight positive side and negative side. And then here, this top image, you can see even more in detail how the oxygen and the hydrogen are sharing electrons here. And then how the actual angle of this molecule is 105 degrees. So what these are called, this sharing of electrons, means that these are covalent bonds. And that's these strong covalent bonds between the hydrogen and the oxygen atoms. Both hydrogens are on the same side of the oxygen atom, so it's not linear in any way, shape, or form. And it's this bench structure that gives it these somewhat special properties. The bench structure results in this, what we call the dipolar, and that's where you've got the negative and the positive being on opposite sides. So all of this feeds into water being somewhat unique. And it all, again, gets back to hydrogen bonding. So previous slide, we were just looking at one water molecule, but what happens when a bunch of water molecules get together? So water has this polarity, meaning there's a small negative charge at the oxygen end and these small positive charges at the hydrogen end. And so opposites attract. And so this small negative charge is attracted to this small positive charge, and this positive charge is attracted to this negative charge, and it starts to orient itself in a very particular way. And so this happens between water molecules. It also happens with water and other ions. And these are called hydrogen bonds. And they're not as strong as the covalent bonds where the electron is actually physically shared. But they give a stronger attraction than molecules, obviously, that don't have any, any way to sort of line up or connect with one another. So hydrogen bonds are weaker than covalent bonds, but they're still strong enough, and they contribute to a variety of things in water. So cohesion, meaning the molecules start to stick together, and this results in high water surface tension. So this is why if you go to pour a glass of water, you can keep pouring the water, if you do it slowly, basically above the rim of the glass, right? Without it spilling. You can make like a little dome. And that's because water has that surface tension. The molecules are holding together. It's also the same reason why insects and things can walk on water. They rely on that surface tension. So the hydrogen bonds also are important for the solubility of chemical compounds in water, so helping things dissolve. Water is that universal solvent, so all of the various ions that come into the ocean from rain or from weathering of rocks or from volcanoes, they end up soluble, so they end up dissolved in seawater, which, and a lot of these dissolved species are used as nutrients or, important aspects of life in the sea. The hydrogen bonds are also the reason water has these unusual thermal properties. And so that's where, we had talked about the specific heat and the latent heat. So this idea that you can pump a lot of energy into water without actually changing the temperature. And so I think the example in the reading is a really good one where it says, it talks about how as long as you have ice in your glass, any added energy, so the sun sitting there on your water glass as you're sitting outside is acting to slowly melt the ice. And it's not actually going to change the temperature of the water. And then, of course, the unusual density of water. And the fact that ice, the solid form, is less dense than water, the liquid form. And so as water cools at the surface, the really cold water sinks to the bottom and starts to mix nicely until eventually a little bit of it freezes. But that frozen water sits at the surface and it doesn't sink to the bottom, which means that bottom water is basically at the coldest temperature water can be before freezing, but it's now protected by a layer of ice that isn't going to sink. And so now that extra sort of cold, no matter how cold the atmosphere gets, you're never going to have the bottom of that lake freeze over, or the bottom of the ocean freeze over. So this is a nice image showing water as the universal solvent. So what happens here is you have sodium chloride salts in their nice crystalline structure on the left. Sodium has a positive charge, chloride has a negative charge. And what happens is the negative charge of chloride lines up really nicely with the positive charge of the hydrogen in the water molecule. And so you end up completely hydrating this chlorine ion. And then the same here with the sodium. So you've got a positively charged sodium, and the negative side of the water just lines up really nicely. And so this sodium and chloride starts to break apart and be surrounded by water molecules, and is then completely what we call hydrated. And just a refresher here, additional sort of interesting properties of water or sort of aspects of chemical oceanography that will keep coming up is that water with nothing in it has a pH of 7, which is neutral. All right, but of course the ocean is full of stuff, so it's not just water, so it's not going to have a pH of 7. And it's important to remember that there's acidity and alkalinity. And so an acid is something that releases a hydrogen ion when dissolved in water, and that is anything with a pH less than 7 is an acidic solution. And an alkaline or basic solution is an object that releases a hydroxide ion in water, and that's a pH greater than 7. And so I wonder if any of you guys actually know the average pH of seawater. It's something we're going to talk about a little bit as we get to, talking about chemical oceanography. You'll get into this way more when you do marine systems. But on average, the pH of the ocean is about 8.2. So the ocean is on average slightly basic or slightly alkaline. And in fact, the alkalinity of the ocean is something that we talk about a lot. Here we go. All right, so I actually have a pH scale slide here. So this is measurements of the hydrogen ion concentration. So this is just a refresher for you guys. And remember also that the pH is on a log scale. All right, so it's not linear. So water in the Earth's system is primarily in the ocean. Greater than 97% of the water on Earth is in the ocean. Quite a bit of it is frozen in glaciers and ice caps. And then all of these beautiful streams, lakes, all the moisture in the atmosphere, all the water we interact with on a daily basis is pretty much nothing in contrast to the size of the ocean. But of course, the movement of water through these various spheres, which we call the hydrological cycle, is really important. And there's a lot of components of the hydrological cycle that impact seawater salinity, and salinity, of course, impacts density. And the hydrological cycle is also responsible for recycling water between the oceans, between the atmosphere and the oceans, and through the continents and the atmosphere and the oceans. And so seawater, the oceans just sort of look like they're always full, but when you think of it from the perspective of a water molecule, the water itself is continually cycling between all these reservoirs. So a water molecule that's in the ocean today can be evaporated up into the atmosphere, it can move over the continents, rain down on the continents, and then eventually make its way back into the ocean. So here, this is a nice image showing the hydrological cycle and that continual motion between the various reservoirs. So you've got precipitation shown here on land, and this also gives you nicely the sort of volume of these various reservoirs. And this precipitation can come down from rivers and run off into the ocean. You can also have groundwater, so that's water that's in the ground here, moving between the ocean and atmosphere. You have precipitation in the ocean, and you can see there's a lot more precipitation that happens over the ocean, but that's also because there's a lot more ocean than there is land. There's evaporation from the ocean. So this is when the liquid water comes up and becomes gaseous water in the atmosphere. You have evaporation from the land as well, not just from the ocean. And again, this number is much smaller, but you have to think about this sort of scale of these two things. And down here, these tables show you, so this is the sort of what we would consider the standing stock, like where's all the water right now. And then this box here shows you the fluxes between the reservoirs. And you'll note here, because it's a flux, it's some sort of movement, there has to be some time component. So you can see here, this is just the percentage, it's just the amount, but this is actually the amount over a certain amount of time. So this is the volume per year. So from the ocean to the atmosphere, 320,000 cubic kilometers of water fluxes from the ocean to the atmosphere per year. That's how you would interpret this. So the standing stocks, are quite large in the ocean, but this cycling is also quite large. This water is moving constantly between these systems. Which leads to the idea of a residence time. So a residence time is, so we talked about that water molecule that's in the ocean for a while, but then it leaves via evaporation and then eventually comes back. So the residence time is the average length of time a substance remains dissolved in seawater. And so you can apply this to all sorts of things in seawater. The things we tend to think about are ions like sodium and chloride. You can also apply this to nutrients, which we'll talk about in a couple of days, like nitrate and phosphates. But the general idea is that ions that have a long residence time tend to be high in concentration of seawater. So that means it accumulates. So the particular ion comes into the seawater and it stays there for a long time. Because it stays there for a long time, it sort of builds up. Ions that have a shorter residence time tend to be lower in concentration in seawater. So that's something that comes in, but it's gone by the time, it doesn't really have a chance to accumulate or to build up in the seawater, because whatever its input is, its output is sort of just as quick. And then there's what we refer to as the steady state condition. And this is actually kind of a terrible definition here, sorry. It says the average amounts of various elements remains constant. But steady state just basically means if you think about a swimming pool and you put the hose in the swimming pool is going to start to fill up if you don't do anything else. And eventually it's going to overflow and you're going to flood everything. But if while you put the swimming pool in, you also open a valve at the other side, And so let's say you fill the swimming pool up, and then you open that valve, and the size of that valve is equal to the hose you put in. So the amount of water coming in from the hose is the exact same amount of water that's coming out the valve. Then your full swimming pool is going to stay full. And if you just looked at the swimming pool, it would look as if absolutely nothing was happening, because you're just looking at this pool that's just filled with water. But in reality, that water is constantly being changed. But what's coming in from the hose is leaving immediately through that valve, right? But it means that the water at any given time, it's actually new water, because this new water has come in from the hose, and then some of the old water has left out the valve. And that's what you would call your pool is then its steady state. So it doesn't mean nothing's happening, because there's lots happening, right? You're filling up the pool with the hose, you've got the valve, there's water coming in, there's water coming out, but it's completely balanced. And so that's the steady state condition. Okay, so here then we've got another nice schematic showing the cycling of dissolved seawater components. So when you think about the residence time of something, then you have to start thinking about, well, where does it come from? So let's say the residence time of sodium. Well, how does sodium get into the ocean? And how does sodium leave the ocean? Obviously, it hasn't been accumulating forever, or there would just be an insane amount. So there must be inputs and there must be outputs. So most things that end up in the ocean get there by river discharge and volcanic eruptions. So volcanoes spew all sorts of stuff, chloride, sulfates, a couple of other elements, and rivers export all sorts of ions, so mostly carbonates, calcium, sulfate, and sodium. You can see here. And so these are things going into the ocean, and they dissolve because water is a universal solvent. And then they do eventually leave. Some of them adsorb onto particles. You can have precipitation. Sea spray can remove things. So sea spray on the coast, things end up being put back on land. And you can have little organisms, so biological things that make shells or skeletons. Think about, corals or things like that. And if those can be buried, then they can be removed from the ocean. And then you also have hydrothermal vents, which we talked briefly about, that are both spewing chemicals out, but also absorbing things from the seawater. So things get into the ocean through rivers, volcanoes, and hydrothermal vents, and things are removed from the ocean through adsorption, sea spray, biological processes, and hydrothermal vents. So the residence time for a given ion will be dependent on these inputs and these outputs. So the residence time is controlled by that. But of course, if the inputs completely equal the outputs, then you've got your swimming pool scenario and you're at steady state. Okay, and that means your concentration isn't really going to change over time.